Hi everyone, welcome back to this virtual class. And I really want to say good morning, but I imagine that when you're clicking this video, you might be in the afternoon or in the evening, so let's just skip that part. And if you're watching this video, I'm assuming that you have finished the first video, and then if you feel a little bit disappointed about the virtual class, believe me, I feel the same way. I never really like my first recording. And part of the reason, I think, is because like when I'm talking to the empty room, when there's no one, my energy level really just go down, really go down, and then I couldn't focus. And some faculties actually gave some pretty good suggestions. For example, they say that you can record 10 to 20 minutes and then kind of stop there and rest a little bit and then regain the energy level. And today I'm going to try that. So that's also one of the reasons that when you're looking at the note, while you have it on your computer, when you're looking at the note, actually I divided our class into several sections. So after each section, I would take a break. But then you wouldn't notice because I'm going to patch all the videos together, so you will still get an hour to an hour 30 minutes course video. Okay, so today, the first section about today is to briefly review what we have talked about last in the last class or last video. Okay, so in the last class, the critical thing is that we migrate from second order nonlinearity to third order nonlinearity. And then just as everything else, at the very beginning of this class, I want to just remind everyone what is our basic assumptions of this class, no matter what order of nonlinearity you're considering about. First is our definition of electrical field of the light. Okay, you have many frequency components, and then the nonlinear equation is that the first derivative of this field and of course if you're at home, if you're watching this video and you're already very familiar with this part, you can kind of skip it, right? It's difficult to do in a real classroom, but really easy to do in a virtual one. Okay, and the linear polarization in this case, we have to write the definition down here because we're going to use it sometimes later. And this is the definition of the displacement field, which if you get rid of the linear term, you put the linear term in the front, then you get the nonlinear polarization. And for third order harmonics, for third order nonlinearity, we have the nonlinear polarization equal to epsilon chi3 and then e to the qubit, basically. Okay, so this is kind of standard. And in the previous class, what we have really focused on are three major conclusions. Okay, the first one is that for chi3, it doesn't require certain symmetry for your material. So therefore, chi3 actually exists in all materials. So this one kind of tells you that chi3 is very general, and then that's one of the reasons that why we should really spend some time on this thing. Okay, and the second thing is that for certain chi3 process, there's no phase matching condition. And then we give one specific example, And that example is if you only have one input to your nonlinear material, if you only have one input and then you only consider one output, right, at omega t frequency. In that case, the third order nonlinearity simplifies into a Curry effect, which look like this. Which looks like your refraction index, okay, is equals to your original refraction index without light input plus a term that's proportional to the intensity of your input light. Okay, and this is derived with one frequency component. Okay, one frequency component. And when you look at the conclusion we get from previous class, this actually looks quite promising because think about this. Okay, first of all, it's very general. You have it in all material, and then second, you don't need to consider phase matching condition, which is great, right? When we're calculating things, we always assume that the phase matching is perfect, and now you don't have to assume that. Well, in some cases, it's just phase matched. And third is the Curry effect. If you look at this equation, this is probably the simplest equation we have ever talked about in this class regarding nonlinear optics, right? So, so the key question for today is that can we generalize this equation for today and next class? Okay, can we generalize to multiple wavelengths, multiple frequency component? Right, so this is a key question. If you can do that, then the third order nonlinearity seems relatively simple because it's just an input and then you change the refraction index, and then you can base on that to derive all your equations. Okay, so the key question we can plot here is that if you have multiple input, multiple output, you consider many waves. Okay, does the Curry effect, does this equation still holds? Right? Do you still have these simple equations? And this is the key mission, okay, for today and for the next class. Now let's migrate into second section. Okay, you might not notice, but I actually took a break for several minutes. So the second section, okay, is that if this is the goal of our discussion, we want to generalize it. Of course, one way to do it is you just start calculating, right? Just start calculating. But that's actually a terrible idea, as you might have already learned in this class, is that whenever you try to calculate something difficult, you should not do it immediately. You should always wait a little bit and then think, okay, what exactly are you trying to calculate? So for example here, look at this equation. What do we mean? But when you look at it, okay, well, if we want to generalize it, the first question we have is that, should we modify this form? Okay, if this is correct, this can be generalized. How should we modify this form? Because when you're generalizing it, then you have, you see here, then your electrical field of your light is now a function of time, okay, and also you have multiple frequency component. So when you say refraction index, do you mean refraction index at a specific time, or do you mean refraction index for a specific frequency? Right. So these are the key questions. Before we even calculate anything, we should actually try to guess what's the correct form. Okay. So of course there are two reasonable guesses here. Of course there's more than two, at least two reasonable guesses. One is that okay, because we derive this from a single wavelength, single frequency. So you might guess, okay, these are wavelengths dependent on frequency dependent. So you can say, okay, the refraction index at a certain frequency equals to n knob plus n2 is just a constant. You can say n knob is also a function of frequency because there's dispersion, right? N knob omega times n2 I omega. I omega means the intensity of the light at frequency omega. Okay, so this might be one possible guess. The other possible guess is that you know that whenever you write something down in frequency domain, you can always link that to time domain because there's a Fourier transform. Right? You guys are electrical engineer, you must be very familiar with that. So the counterpart of this is that your refraction index, not at a specific frequency, but at a specific time, okay, equals to n knob. Well, the refraction index, the original refraction index is not changing with time, right? Because it's material sitting there. Okay, so here, okay, we don't put time here. But then the question would be, okay, if you look at why there's a frequency here, why not here, right? So the problem is, what's the definition of n knob if we don't add the time here? Which frequency are we referring to? Okay, let's leave this open here, plus n2 IT, right? The intensity of the light is apparently a function of time, right? Because all these different frequency components, they will interfere with each other. They will create a bit node, okay? And then sometimes it's bright, sometimes it's dark. It's just like a young. If you have two wavelengths, then you will have a bit node. That's just like a young double slit experiment, okay? So out of these two guessed, which one is correct, right? Which one is correct? Because this is critical. If this is correct, then we have probably one way to derive it. We focus on specific frequency components. If this is correct, then probably we need to carry all frequency components because there's a time. Okay, the time, the intensity at a certain time is related to all frequency components of the light. Okay, so intuitively, based on what we have learned in nonlinear optics, we can see that this one must be wrong, okay? Because the key of the nonlinear optics from the second order nonlinearity, for example, harmonic generation, frequency sum, frequency difference, parametric oscillator, we all learn one thing is that you can convert light from one frequency to another, okay? So the refraction index at omega, at frequency omega, can not only depend on the frequency, on the omega components itself. It must be related to other frequencies. Right? For example, another way to look at it in a more mathematical way is that there's an E qubit term here, right? So when you do E qubit of this thing, all the frequencies are going to be mixed together, okay? So it's almost impossible to imagine how your refraction index at the frequency omega only depends on the intensity of frequency omega. So this one, intuitively from nonlinear optics, is wrong, okay? So if I would guess, of course we know the answer. I know the answer, so I'm not really guessing, okay? If you are the researcher, you really want to guess, okay, you should guess this one. This one makes more sense because it says that refraction index at a certain time depends on the intensity of light of certain time. And the intensity of light, because intensity of light proportional to the E T Z, okay, because it's composed of, it's a function of all these frequency components. So at least, okay, at the very least, this definition or this form of current nonlinearity is not in conflict of what we have known or what we have known in nonlinear optics. Okay, so there's no conflict. Okay, so this one is our guess. Okay, so let's move on to section 3. This section is a little bit long, and hopefully I can keep energetic at the end. Okay, so to derive from a single frequency to a generalized case with multiple frequency components of the Kerr effect, the only way we can do that is by looking back into the equations that we already know, right? So the definition of your electrical field inside the medium, nonlinear medium, is quite straightforward. There are multiple frequency components. This is just as usual, okay? And then the equation that these components they follow is also very standard, okay? This is a standard nonlinear equation. And the only thing that's really unknown for us or new to us is how do we calculate this third order nonlinearity term, okay? E to the qubit, right? So here what we can do is that first, okay, your frequency, your electrical field, when we're doing square or qubit, both the negative frequency term, okay, we call it negative frequency term here, and its conjugate, both of them are useful, right? Because when you're doing square, right, this one can multiply with the conjugate and produce some terms. So one way that we should, just to make our calculation a little bit more obvious, is to write down the negative frequency term and its conjugate separately. Okay, here I use L, but actually it can be J because this is just an index, and when you do square or qubit, these two never mixed up. Positive frequency minus IKLZ. Okay, so or in a very short term, you can write it down as sigma j. See what I do. Okay, sigma j plus sigma L conjugate. Okay, this is just to make our life a little bit simpler. Whenever you see sigma, you know that okay, there's inside there's a different frequency component, and this conjugate just denotes the complex conjugate used here. Okay, so then let's look at how we calculate e to the third. E qubit. And just like before, we say that to simplify the math, we assume that all the polarization or the vector here are pointing towards one direction, so that we can get rid of the vector here. Okay, epsilon chi 3 e to the third. And because this is just a constant in the beginning, so we don't really need to carry that all the time. We just put it back at the end of calculating this nonlinear polarization. Okay, so e to the qubit, then you can, if we use this notation, carry on with this notation, then we get this. Or you can write down as, okay, EJ can write down as this. Now, by looking at this, you can see there's at least, well, there's actually 4 different types of terms. Okay, the first type is that when you're doing E qubit, okay, each one of these has all these electrical field components. So when you pick EJ, or J1, L1, sorry, J2, L2, J3, L3, okay, they're independent. Okay, so what will happen is that you can pick any one of the electrical component here and multiply with anyone here and multiply with anyone here. Okay, so of course there's a mathematical way to really expand this and then using notations, but those are too technical, so I would actually technical and not very easy for us to simplify things. So I want to do it a little bit differently here. Okay, and as a very obvious observation, you can see that okay, there are 2 different favors, right? One is negative frequency components, the ordinary one. The other one is its conjugate, and they will produce distinct results. For example, if all 3 are coming from the negative frequency components, then what you will have is the term you will have is ej1, ej2, ej3, e to the minus I omega j1 plus omega j2 plus omega j3 t, and then of course ik j1 plus j2 plus j3 z. And what is this? This is just, you know, some frequency, right? Some frequency. Or you can say, okay, this is like the third order harmonic generation. So this one, as we know, when you're summing all this frequency, the frequency actually change a lot, right? It can almost it's likely to be tripled. So also you see the phase is adding up, the k is adding up. So this one, for this one to work, the 3 sum frequency to work, of course you need phase matching condition, and that one is really not in our discussion here because we assume that, you know, all this high order, all these harmonics, all this large frequency change is difficult to obtain. So we let this goes to 0. Okay, assuming its phase matching is violated. Okay, and in real experiment you will see things very, very similar because this indeed require a very strict phase matching requirement. And then the second one is that, okay, the second one is, of course, it's complex conjugate, right? You can pick all 3 conjugate terms here. So it will be EL1, EL2, conjugate, EL3, e to the I, omega L1 plus omega L2 plus omega L3, t plus I, this is minus L1 plus KL2 plus KL3 Z. Okay, here also conjugate. So as you can see, this is also just a sum frequency, but it's just a conjugate of the previous one since J and L are general indices. Okay, it go from, you know, one frequency to another frequency. Okay, so this one goes to 0 as well with the same reason. Okay, same reason. And then what's left are 2 type of term now. Okay, the 3 is that you can think about it. Okay, if I pick 2 positive term or 2 minus frequency, negative frequency term, J1, J2, and then I pair it with one of the conjugate, then what will happen? Okay, it's 2 E conjugate. Okay, we call it this type of term. And then well, there are 3 ways, right? Because you can, the first 2 is normal, the third is conjugate. You can also get the second one is conjugate, and the first and third are normal. You can have the first one as conjugate, and second one and third one are normal, right? So there are 3 ways to do this, and eventually you can imagine there must be a factor of 3. When we finally formalize this. Okay, so we take this as example. We pick the first one, the second one as normal, the third one is conjugate. Then you will get EJ1, EJ2, EL3 conjugate, and the frequency is I minus I omega J1 plus omega J2 minus omega L3 T plus I K J1 plus K J2 minus K L3. Okay. Okay. So when you look at this, you will see, okay, the frequency is not that much different from omega j1, right? Because what you're doing is that you're simply adding omega j1 with the frequency difference between j2 and L3, right? So if you assume all the frequencies are very close to each other, then this one will also be very close to each other, right? So we can draw a picture here. We can draw a picture here. If this is omega frequency, right, then you can have, okay, one component, the other components, and then this is let's say J1, 2, and 3. So what it does is that if this is J1, this is J2, this is L3, then what it does is that this one will multiply, will add the frequency difference between J2 and L3, okay? And in this case, L3 is larger than J2, so this one is a negative number, so it will generate a wave here, okay? So this frequency would be omega J1 plus omega J2 minus omega L3, okay? So you can see this, it generates a new frequency based on this, but this frequency is very close to the original 3 frequencies. So from this point of view, this process is very distinct from this previous 2 process. It's not a sound frequency, it's not dramatically changing the wavelength, it's simply adding nearby wavelengths or nearby frequencies. So these are the terms, this is the term that we need to focus on. Okay, and the fourth one, of course, you can imagine is the conjugate of this one, which would be 1 positive component and then 2 conjugate component. So not 1 normal components and then 2 conjugate components. And then here we use an example. We can pick J1. The first one is normal. The other 2 are conjugate. Then you get EJ1, EL2, EL3, e to the minus I, omega J1 minus omega L2 we can, because we have 2 positive terms, so we can let here be positive. Okay, we can do it differently here. We write down the positive frequency first, omega L2 plus omega L3 minus omega J1. Okay, same for the phase term. We have K L2 plus K L3 minus K J1. So you see here that it's a positive frequency term, and the frequency is sum of 2 frequency minus another frequency. Exactly the same form as the previous one. So these 2 are actually coming from the same source. It's just the complex conjugate. The 4 is just the complex conjugate of the 3. Okay, so these are the terms we are going to consider. And in the second half section, I'll describe how to summarize these terms into, into a better form other than writing it as like this, right? So like when you look at this, you don't even know how to calculate. Okay. Okay. Now let's try to finish this section, and I need to make some room on the board. And I realized last time the board was really messy. So let's see. Let's plan a little bit ahead. I guess everyone can remember this. We need Curry effect. We want to derive Curry effect, which is extremely simple equation. And let's remove this. Okay, let's make the room for this. And it's quite interesting today. It's really sunny in Charlottesville, and then I'm in my basement, so there's actually a lot of light coming from the side, and it's really benefiting from this, dividing the class into multiple sections. Otherwise, my camera would have already been overexposed. I actually adjust each time I go back to the camera to turn it on. I actually have to readjust the shutter speed and also the aperture, so that otherwise everything would be purely white. And this is another interesting topic, well, although it's irrelevant to this class, is that when someone pick up, well, now everyone is a photographer with iPhone, okay, but when you pick up a real camera, for example, Canon is actually better. If you pick up a Sony, then the first thing you realize is that, okay, that's so difficult to use. Okay, it's not intuitive, and then there's a lot of way to mess up the final result. And for example, to set up this recording, camera, I actually have to tune my voice here into manual mode, because otherwise the amplification of the voice is going all the way. And also I need to adjust the white balance, adjust other things. But when you do with the iPhone, it seems that Apple really spend time, or other smartphone company really spend time on optimizing. It seems that Apple really spend time to optimize all this to make it accessible to everyday use. And I really hope that some of the camera company can do the same. Otherwise, no one will be using them. Like if Apple has a camera, I would never buy Canon or Sony. Okay. Now let's keep going on here. Okay, the goal here is, okay, we know that e to the qubit is like this, but we want to reduce it. We want to get rid of all these terms because they correspond to harmonic and some frequency, but only keep these terms. Okay, and we want to also have the parameter the coefficient correct, right? So as I briefly explained, because each of this, there are three ways to get it, right? You have a conjugate term. The conjugate term can come from the first bracket, second bracket, or third bracket. So there should be a factor of 3 here. So quick way to look at it is that if you say this is A, this is B, okay, then you can have A plus B to the third. Okay, of course this is wrong. Okay, but we can use this to understand this. So you have A to the third, which is this term is your harmonic and sum frequency generation, and then you have 3A squared B. Okay, this is this term here, and then there's a factor of 3, and then 3AB squared. This is its conjugate, also have a factor of 3, and then finally you get B to the qubit. Okay, B to the qubit is this term, the conjugate of some frequency. And because in here we neglect this and that, so you can kind of imagine that the final solution would be the sum of this term multiplied by a factor of 3 plus its conjugate. Okay, that's just a guess. And let's see how we can justify this. Okay, to justify this, of course, one way to do it is just calculate it. Okay, by changing the indices, you can actually prove it. That's correct. But here we use a little bit intuitive way to do that. Okay, suppose we're only looking at one frequency components, right? Because all this term after all this, you actually get a frequency called omega j plus omega j2 minus omega L3. Okay, so let's say we look at finally the frequencies omega mu. Mu is the indices. Later we'll talk about the strict definition of mu. Okay, if we use this, then okay, suppose there are 3 frequencies. Suppose there are 3 frequency components that can satisfy omega mu. Right? Suppose omega mu equals mu1, mu2 plus mu2 minus mu3, right? It's kind of intuitive. Suppose we just look at these frequency components. Just look at these frequency components. And then just look at the frequency components coming from these three waves, okay? Okay, so let's keep explaining how this works, okay? So suppose we focus on one frequency component, that's omega mu, equals to, well, there's a way, okay, this can produce omega mu is omega mu1, omega mu2 minus omega mu3, okay? And the critical thing here is that where does this 3 come from, right? The factor 3 come from. It comes from the fact that, okay, these two are fine, they're all positive. This one has to come from the conjugate terms. And then the conjugate term, omega mu3, can come from here, or here, or here, right? Because these are sum. So in here, there's omega-3. In here, there's also omega-3. And also in here, there's another omega-3, right? Omega mu3. So that's actually the reason, okay, why we can write this term down as sigma mu1, mu2, mu3, okay, 3 times e mu1, e mu2, e mu3 conjugate, and then e to the minus I omega mu1 plus omega mu2 minus omega mu3 t plus I k mu1 plus k mu2 minus k mu3 z. Okay? And you're thinking, okay, but we previously label everything J1, J2, J3, L1, L2, L3. Think about this, okay? You can actually write these terms 3 ways, right? One is J1, J2, L3 is conjugate. The other is L2, okay? You can either be EJ1, EJ2, EL3 conjugate plus, okay, EJ1, EL2 conjugate, EJ3, and plus, finally, the first one is conjugate, EJ2, EJ3. Okay? And J1, J2, J3, omega 1, omega 2, omega 3, right? So there are 3 terms that are equivalent to each other. And because all these are just indices, okay, and they're independent from each other, so what you can do is that you can write them as a complete sum, mu1, mu2, mu3, corresponding to here. And then because there are 3 of them, so put a factor of 3 in the front, okay? And then if you have doubt about this result, what you can do is that you can actually calculate that by using indices. And then it's not that difficult. It just costs a little bit of time. And so that's why we're not going to repeat it here. Or we're not going to talk about it here. Okay. So after that, let's see which one to erase. Okay, we can erase it here, this one, because we'll start to use this equation. Okay, erase here. So if we summarize what we have just obtained, is that what we say is that for one of the frequency component omega mu, okay, let's make it clear, k mu is just an indices just like j, okay? If you want to keep using j, that's perfectly fine. Plus its complex conjugate equals to, there's coefficient mu knob, and then for the chi, for the nonlinear coefficient, there's epsilon chi 3 in the front, and then followed by e to the third, which is this one. So you have a 3 here. And then you have the derivative, twice derivative of the time term, right, which will give you minus I squared will be minus sign here, okay? And then the frequency is omega mu1 plus omega mu2 minus, let's rewrite this a little bit, equals to minus 3. 3 come from here. Epsilon mu naught chi 3, okay? And then there's the frequency term. You do frequency derivative. While you do time derivative of this, okay, there's frequency term omega mu1 plus omega mu2 minus omega mu3 square, right? That's the second order time derivative come from here. And then you have E mu1, E mu2, E mu3 conjugate exponential minus I omega mu1 plus omega mu2 minus omega mu3 t, and then and then the phase term I k mu1 plus k mu2 minus k mu3 z. Okay. And then here, because it's sum, right? There's a sum here, so we'll put it down here. Sum mu1, mu2, mu3. Okay, so the sum is that mu1, mu2, mu3 goes through all the possible frequencies as long as there's a constraint. Okay, as long as omega mu equals to omega mu1 plus omega mu2 minus omega mu3. So the other way to think about this is that you can actually go through mu1, mu2 can go through anything, okay? But as long as you choose omega mu1 and omega mu2, your omega mu3 is actually fixed, right? So this constraint, whenever you have a sum, the constraint actually eliminate one of the free indices, okay? So this is, okay, let's put it here. And this is for one frequency components. And let's make it clear what is mu, right? You have multiple frequency components. Okay, then this is omega. Right? The mu is just the indices that you use to label them. For example, you can label this as 1, 2, 3, 4, 5, 6, okay, and keep going. Or you can label this 0, 1, 2, minus 1, minus 2, minus 3. Or you can just give it random number, that's fine. Okay, and when we do sum, what we do is that, okay, omega mu1, then it's this plus omega mu2. You can say omega mu1 is 1. Mu1 goes through 1 to 6. Mu2 also goes through 1 to 6. And then mu3, whenever you choose mu1 and mu2, mu3 is fixed because you have to satisfy this condition. Okay, so this is the general equation. Okay, this is the general equation for third order nonlinearity when we neglect harmonic generation. Okay, you can write it down as something equals to a sum, and this sum is relatively easy to handle. And there's actually, later I will introduce, well, in the next class I will actually tell you about this. Is this one, if you do Fourier transform, can go back to, if you look at it, right, this looks very close to E times E times E star, which would be, sorry, I forgot the complex conjugate. Okay, there's complex conjugate here, complex conjugate. It's very similar to, okay, normal term times this term, and it actually looks like this, right? If you take a closer look, it actually looks like this, and then you can actually use Fourier transform in a smart way that to convert this back to the Curry effect. So this is where we're going, and this term, just to justify itself, this term makes a lot of sense because it looks like the current nonlinearity term. Okay, this is this section, and I'll take a break, and then we'll come back. Okay, now let's come to the fourth section. And one thing I'm keep watching my camera, okay, other than the exposure, the aperture, the other thing is that the battery. I actually have another better camera that I thought I could use, but then I realized that camera's battery is actually very small, and then it can never record more than 1 hour. Okay, so okay, now let's come back to the class. And so this is a general equation, okay, we derive, which is great depending, well, whether you're scared by this or not depend on your mathematics, right? Like how experienced you are to handling things like this. Like for me, this is great. Whenever you have a sum of something multiplied together, this is something easy, relatively easy for me to handle. Okay, and then but instead of going directly into here and then calculate everything out, and one thing we could do is just to analyze, okay, analyze what these terms really means, okay, what consequence or what phenomenon we can expect from this equation, okay, and also we can check whether this equation is self-consistent. So the first thing is maybe I can leave it here. This one, it's a relatively simple case. Suppose, okay, we here we say mu. Mu is a label, right? And then it sums. Mu is a label. It goes through all the possible frequency components. Suppose, okay, mu could only be 1. Okay, I'll say mu 1, mu 2, mu 3. All of them can only be 1, meaning there's only one frequency component. This will return to our previous class situation, right, where we only consider one wave. And let's see what this will give us, right? And the left-hand side, just this is a common term, we don't care about this. And let's look at this side, okay? So the right-hand side will equal to minus 3 mu knob epsilon knob chi 3, which is also just a normal term. And then this one, we know this is omega mu. Mu equals 1, so omega 1 to the square. Fine. And then all of these terms are the same, right? Mu 1, mu 2, mu 3 are all 1 because there's only one possible frequency and there's nothing to sum about. So you have E1 times with its conjugate, so it's actually E1 square, amplitude square, and multiply with E1. And its frequency is the same as omega mu, so minus I omega 1t. And this k, because mu 1, mu 2, mu 3 are all the same, so these two cancel each other, you're left with ik 1z, right? So if you look at this, okay, you see, okay, this is just your wave, and then this part change your refraction index, right? And then you go back to, well, and then this result actually returns to the Curry effect where there's only one frequency component. So this simple case at least tells us that this equation, is what's the word? God. It's self-consistent. Yes, this equation is self-consistent. One thing I have to say is that I haven't spoke English since the last recording of the class because, like at home, I don't need to speak English, and sometimes I realize I start to forget about words. Okay. Oh, also I speak English with my students, but we only have a weekly one meeting per week, so yeah, there are 3 opportunities for me to remind myself how to speak English, okay? And then the second simplest case, you can imagine, second simplest case would be there are 2 waves, right? There's omega 1 and there's omega 2. Okay, you can label this mu 1, mu 2. 2 waves. And the reason we look into 2 waves is just to see that, okay, what terms there are apparently several terms exist here, and then what do they do? Okay, what do they really do to the to a system, right? So for this one, the left-hand side will have two components. Okay, let's say the left-hand side of this equation equal to 2ik1 e1 e to the minus I omega t plus 2ik2 e2 okay. Oh, the other thing I want to mention is that I know, like, at least maybe for international students or for students who live alone, not with their parents, if you don't have a roommate, you're living by yourself, you actually don't have a chance to talk at all. Okay, and that's, you know, from a mental health point, that's not a good situation. And so I actually, you know, recommend you guys to form, you know, study group with your friends, not for this, well, not maybe not for this class, but for other class. So at least to keep a common, well, to keep a regular and constant human interaction, right? This way, like, you know, it just feel much better. And then I remember that in the longest time that I haven't talked to anyone is probably, the longest period of time is probably 10 days or 14 days. It's a time that it's in my after my second year in college, and I was preparing GRE test, you know, in Beijing. I think so, in Beijing. And then, you know, my family is in Canton. Okay, and then it's just so hot in the summer, and then there's no air conditioning at that time. Right now, there's air conditioning. So I have to, you know, book a hotel. Otherwise, it's like, if you couldn't sleep, then how can you take a test? And so I was in that hotel room for 10 days. Okay, the only one I can talk to is the person in the restaurant when I order food. And then I didn't talk to anyone for 10 days. And then, and based on my GRE score, I can say that that's not healthy. Okay, it doesn't help my GRE by not talking to anyone. I should talk to everyone. I should talk to a lot of people, and also in English, in order to prepare that exam. Okay, and this is the left-hand side. It's standard. Let's look at the right-hand side. Okay, for the right-hand side here. Okay, because there's two waves. That's true. Okay. So you can write down two group of terms. One group is that you have, okay, this term summa s omega 1, and the other term is this, the other group is this summa s omega 2. But think about this, the symmetry in the system is that omega 1 and 2, they're just two waves. And we give them this label 1 and 2 just based on our, you know, preference. You can say this is 2, this is 1. It doesn't change anything. So whatever terms you get for omega 1, you can switch indices from 1 to 2 and 2 to 1. That way all those terms becomes the terms for omega 2. Okay? So with that in mind, okay, to save our time and to simplify the process, what we do is that we only calculate the terms associated with, you know, e to the minus I omega 1. Eventually this terms goes to omega 1. We only calculate those terms, and then we mirror them to omega 2 and get the complete solution. Okay, so for the omega 1, now let's think about it. What terms can give us omega 1? Right, there are, you know, the straightforward way is that omega 1 must be omega 1 plus omega 1 minus omega 2. Sorry. Plus omega 2. Well, there are two ways. Okay, one is omega 1 times plus omega 1 minus omega 1. Right, so this one is equal to omega 1. And you can imagine, okay, three waves are the same. So we'll just return to something like this. And the other one is omega 1 plus omega 2 minus omega 2, right? Minus omega 2. Then these two omega cancel each other and you're still left with omega 1, right? So for this case, you will have to have, because all three waves are the same, so you have mu1 equals mu2 equals mu3 equals 1. That's a case that gives you omega 1. That's the first case that gives you omega 1. For this one, this possibility, you have two possible situations. First one is that the minus sign is always omega 2, right? So the omega 3 has to equals to 2, right? So this term, the E mu 3 conjugate is always omega 2, okay? This one is always omega 2. But then here, these two, they are interchangeable, right? You can write down as omega 2 plus omega 1 minus omega 2, right? It doesn't change the result. So for this one, you can have mu1 as 1, mu2 as 2, mu3 as 2, right? For this one, you can have mu1 equals 2, mu2 equals 1, and then mu3 equals 2, 2, 1, 2, 2, 1, 2, okay? 2, 1, 2. And these two terms are exactly the same, but they just, because this is a sum, right? So you need to count all the possible situations and sum them together, okay? So if you take this into consideration, then, well, if you sum all these three terms, then what you see is that you have minus 3 mu naught epsilon log omega 1 squared chi 3, right? Because here omega mu1 plus mu2 minus mu3, we let it to be omega 1, so this term is common now, times, okay, times the first one, 1, 1, 1, okay, 1, 1, 1, so it will be E1 squared times E1, okay, and then the frequency term here is e to the omega 1. Now the phase term, because it's k1 plus k1 minus k1, so it's k1. Okay, so this is the first term. If you look at it, it's exactly the same as this is a multiply. Okay, this is exactly the same as your self-phase modulation term here. Okay, and then the second term, you see that mu1 equals 1, mu2 equals 2, mu3 equals 2. Okay, this one would be mu1 equals 1, so E1, mu2 equals 2, so E2, and then mu3 equals 2, E2 conjugate. Okay, so this one you can because it's E2 times its conjugate, so you can simplify this as E2 square. Okay, E2 empty square. And to make it look a little bit like this, we can move the E1 from the left to the right. Okay, it's the same thing. Okay, what we do is just this term original is E1, E2, E2 conjugate, and we change the order. Okay, make it E2 empty square times E1, and then the frequency term here. This one is the same, minus I omega 1t. Okay, now let's pay a little bit attention to the phase term. So the phase term would be k1, okay, mu1 is 1, k1 plus k2, right, k2 minus k2, right? So you have k2 minus k2, so they cancel each other. So you are left with I k1z, okay? This is the second term corresponding to this one. Now the third term here is, the third type of term here is this one. mu1 equals 2, mu2 equals 1, mu3 equals 2. Okay, and you can check this, but you can just write it down as E1, mu1 equals 2. So this is E2, E1 times E2's conjugate, right? Conjugate. And again, you can reorder this. You can just say E2, E1, E2 conjugate, right? You can move this one to the back, and E2 conjugate becomes E2 amplitude square, and then you are left with E1, okay? So this term is also E2 square, E1. Okay, and then the phase term, the frequency is, you can check, is also omega 1, and then the phase term is the same, IKZ. Okay, so if we are to, okay, so we can sum up a little bit. Right-hand side, of course, everything is conjugate, okay? Also left-hand side, conjugate. Okay, so right-hand side here, what we have is minus 3 mu knob epsilon knob omega 1 square chi 3, okay? And then E1 square, amplitude square, plus 2 of the E2 amplitude square, okay? And times E1 e to the minus I omega 1t plus I k1z plus cc, okay? So this is just for omega 1 term, okay, for omega 1 term. And then for omega 2 term, what we can do is we keep writing down, okay? For omega 2 term, you just switch, switch 1 and 2, okay? Then you have switch the indices, so this is omega 2 square chi 3, okay, E2 square plus 2 E1 square E2 e to the minus I omega 2 t, okay, so you get the complete equation. At least for the omega 1 and omega 2 term, okay? Omega 1 and omega 2 term, if you only consider these two waves. Later we'll talk more about this, okay? And what you realize here is that if we know that this term, first of all, this frequency term, okay, you have to, well, if you write down the equation, it would be, oh, the left-hand side term is wrong. So partial z, partial z. Okay, so when you're solving this equation, you know that, okay, each frequency components, you solve the left hand side and right hand side the same frequency component. If they belong to different frequency component, then the average is actually 0, so you don't have to consider that. So if you look at this, okay, omega 1 term here, and this is just the wave itself, right? The electrical field itself, and in front of it, it times two constants here. One is the electrical field of itself, amplitude square, which is the same as self-phase modulation Kerr effect. The other one, this one is interesting. This one is the wave, the amplitude square, or the intensity of the wave, of the next wave, of the second wave, okay? And there's actually a factor of 2. So what it tells us is that if you look at delta n, if you look at refraction index in this case, you will be n naught plus, okay, plus n2 I1. I1 is the n2 is just a coefficient. It doesn't mean n2 for the second wave. I1 is the intensity for 1, the first wave, and then there's a factor of 2, and 2 I2. I2 is the intensity corresponding to the second wave here, right? Because the first one, if you change the refraction index, the second one is also just a number, right? It also should change the refraction index. And not only that, it changed twice as large as the original one, okay? And this one might be a little bit surprising to you, but this is called, this term here is called cross-phase modulation. Okay, this is self-phase modulation, as we already know. So self-phase modulation meaning the refraction index change is induced by your own wave. Cross-phase modulation means the refraction index change is caused by it's caused by another wave. Okay, this is cross-phase modulation. And there's actually, the cross-phase modulation is usually have a factor of 2. It's larger, okay? Some people would say, okay, the cross-phase modulation is twice as much as self-phase modulation. That is not correct. You might see here is correct, but the real reason is that here we assume it's plane wave. So when we assume it's plane wave, those two waves are perfectly overlapped, right? If you think about it, if one wave is propagating, okay, this side going through here, the other way is going like this. If they don't have spatial overlap, then there's no reason that the second wave can affect the first wave. So in the actual calculation, if you're not using plane wave, then there should be an overlap factor here. So if they're perfectly overlapped, then you're indeed twice larger. If they are not overlap at all, then this factor goes to 0. And so the factor will look something like this. Okay, the factor would be eta integer e1 e2, okay, dx dy, because it's cross section, divided by e1 squared dx dy. So it's normalized, right? This is for 2 to 1. Okay, it's normalized because this way, if they are not overlap, then it's 0. If they're perfectly overlap, e1 equals e2, then this one is cancel each other, so you have an overlap factor of 1. Okay, so this is something to a little bit. I want to be very clear about. Okay, the 2 factor here is because of the 2 factor here comes because when you're doing the choosing the indices, there are 2 possible ways to produce cross-phase modulation. So there's why you have the 2. Okay, and then it's not always just 2 times this, because you have to consider there's an overlap factor. In this class, because we always use plane wave, then it's fine, we just keep the 2, and there's nothing else here. Okay. And cross-phase modulation, you might wonder, okay, is this really true? Because think about it, it's counterintuitive. You think that, okay, if I'm changing the refraction index, why is another wave would change more than what I can change to myself, right? It's like I'm propagating, I'm doing all the work, and then I only change refraction index by 1 portion, but I'm changing the other wave by 2, right? So it's not intuitive, but fortunately this is true. This is the math that's showing you this, and I can tell you guys this has been verified in many experiments that the factor of 2 is real. Okay, I can give you one example, which is an experiment done very recently. This factor of 2 was verified like many years ago, but there's a very recent experiment that kind of it's really interesting. I mean, I think published in 2017 or 18. Okay, so here suppose we have a ring resonator. I'll tell you what this factor of 2 would do. A ring resonator. The ring resonator, you can imagine is that you have a piece of fiber, and then you connect the start to the end, right? So that the light can keep going and keep going and keep going. And then you bring another fiber very close so that the light can, go from this fiber to that fiber because of the evanescent field coupling. Okay, so for a ring resonator, typically there are 2 mode. We say normal mode. One is, or two ways that the light can propagate. One is you have clockwise, okay, propagation. The other one is you have counterclockwise propagation. And if you assume that the Earth is not rotating, or the Earth's rotation is very small, then these two modes should be the same, right? It's like there's a symmetry here. You're going forward and you're going backward. They're exactly the same. Okay, so when you're looking at this resonator, the resonator is just like a pair of mirror, right? They only support certain frequencies. So the frequency would be, or certain wavelengths that, after one round trip, the change of phase should be 2 pi multiplied by its integer that is supported by this resonator, so that you have constructive interference, just like the Fabry Pro cavity we discussed before. Okay, so what you will see is that, okay, you can say, okay, there's omega CW, that's the eigenfrequency or the frequency supported by the resonator, will have to equal to CCW, right? When there's no light inside. When there's no light inside, just because there is rotational symmetry. And when you have the light coming in from the clockwise situation, then you will see, okay, the refraction index change in clockwise direction would be N2 times, right, times I clockwise, the intensity of the clockwise. What this would do is that it will change, it will push its frequency. If this is clockwise omega, this is counterclockwise omega. Okay, so it will actually change your refraction index, that change the speed of light inside, and thus shift your frequency. So if you have this refraction index change, then what will happen is that it will shift. Okay, it will shift your frequency to the left by a little bit. Let's say by delta omega. Okay, but if you look at the counterclockwise direction, right? Because this wave because this one is self-phase modulation, but if you look at the counterclockwise direction, then it becomes cross-phase modulation, right? It's a clockwise light change the reflection index of the counterclockwise light. So this one becomes 2 N2 ICC CW. Okay, so your refraction index change of the counterclockwise direction is actually twice as much as the clockwise direction. So what that would mean if when the refraction index change is small, your change of frequency is always proportional to the change of refraction index. Now what it means is that your counterclockwise light, okay, counterclockwise direction, the resonance frequency that's supported by this ring resonator shift twice as large as your clockwise direction. This is very weird, but it's actually true, and then people actually do experiment about this. So the clockwise light is very intense, okay, and then they shift the resonance frequency, and then people send in a very small counterclockwise light. Very small, the power is very small so that you can kind of neglect it, the effect of phase modulation. And people indeed see that, okay, the counterclockwise light, the wavelength, the resonance frequency is shifted by twice. Okay, so this is actually verified in experiment. Now you can think about it, whether this is something useful or not. Okay, it's actually, what it does is that it reproduces something called reciprocal, non-reciprocal device, which means, okay, if you send a light in, okay, and then some of it is reflected back, and the reflected light will see a different resonator because the wavelength is actually shifted. So this one can be used as an optical isolator But of course, it's not a very good one because it's only selecting certain frequency. The ideal isolator is that no matter what wavelength, as given in a wavelength range, okay, the light can only go through but not reflect it back. Okay, but this one is kind of very interesting idea, and then there's more theoretical study on this. Talking about, okay, this is a type of symmetry breaking, and how is that associated with certain research work, certain applications. Okay, so this is the takeaway here is that there is cross-phase modulation. Okay, not only self-phase modulation but also cross-phase modulation, and this cross-phase modulation is real, verified by many experiments, and then we should and sometimes it could be quite useful. So before I let you guys go today, well, you can actually go and then come back in a day or two. It's a YouTube video. So, but before we go, I want to finish this two-wave section because there's one more effect, one more very important effect that can be seen from this two-wave situation. And believe me or not, my energy level is very low now. This is actually the third cut. I tried the first 2 times, and then I get stuck and I couldn't finish the sentence, so I have to stop the camera and then re-rolling again. Okay, so let's try to get the picture out. Okay, in 5 to 10 minutes. Okay, so the two-wave situation, what we do is that, okay, we say there's 2 frequency components, and then we plug in, okay, and then of this nonlinear term, we see there's self-phase modulation, which is your refraction index is changed by your own intensity, okay, and the cross-phase modulation is the refraction index of a wave is changed by the intensity of another wave, okay, it's cross-phase modulation. And there's actually a third case which was kind of hidden and we didn't really talk about it, is that when you plug omega 1 and omega 2 in here, okay, in here, it actually would generate new frequencies, okay, it actually would generate new frequencies. It doesn't just produce omega 1 and omega 2, it actually produces omega 3, omega 4, and all types of frequencies. Let's take a look here, okay. So if we say new frequency, cis, okay. So the idea is that, imagine if we let mu1 equals mu2 equals 1, okay, but mu3 equals 2, right? So this produces a wave that has a frequency of omega 1 plus omega 1 minus omega 1 plus omega 1 minus omega 2. And let's call this frequency, apparently it's, this doesn't equal to omega 1 or omega 2, unless omega 1 equals to omega 2 itself. So let's define this as omega 3, okay? So you can generate new frequencies. And let's see where this frequencies, where exactly is this frequency on this plot. And to see that, one thing you can do is that here you have 2 omega, then this equation also is equivalent to omega 1 minus omega 2 equals to, we say omega 2 is larger than omega 1, so what we can do is we can move here, okay? So move the minus omega 2 to this side, so omega 2, and omega 3 to this side, so omega 1 minus omega 3, omega 1 minus omega 3 equals to these 2 terms move to the right and change the sign, so omega 2 minus omega 1. Okay, so this is kind of interesting. The frequency difference between 2 and 1, okay, 2 and 1 is the same as the frequency difference between 1 and 3, okay, between 1 and 3. So you can imagine here is your omega 3, right? the frequency separation between 1 and 3 is the same as the frequency separation of 2 and 1. Okay, this is quite interesting. And this is not the only frequencies you will generate. The other one is you can kind of imagine, right? You can flip the role here. Can omega 1 equals mu 2 equals 2, and mu 1 equals 1. Okay, so this one will give you omega 2 plus omega 2 minus omega 1, and we can define this new frequency, give it a name called omega 4. Okay, and then you can see that omega 2 minus omega 1 equals to omega 4, right? Move another omega 2 to the left, or to the right hand side, this one. So the frequency difference between 2 and 1 is the same as the frequency difference between 4 and 2, right? So you have here. Okay, so it's very interesting. So from 2 wave, you can generate another. From 2 wave, you can actually, sorry. So this is actually very interesting. From 2 wave input, you can generate another 2 wave, and then the frequency separation is the same. It's the same. So let's get this picture here. Okay, if you input 2, then you generate this 2, and then they are all equally distanced on frequency. So let's really look at this situation. I kind of moved the figure there so that we have more space. Okay, so what is exactly is this, situation, right? What exactly happened? So if you look at here, okay, suppose we get omega 3, the frequency omega 3 term out. What we have is some coefficient partial E3 partial T Z. Okay, that's the left hand side equals some coefficient, and then you have E1, E1, E2 star, okay, and then exponential term, right? So when you look at this, what you can do just to analyze this result is that you can multiply, E3 star, E3 conjugate on both sides. And then if you kind of remind yourself is that, the last time we do this is to verify energy conservation or power conservation in harmonic generation. So when you do this, okay, you see E1, E1, E2, E3 star, okay? And of course there's E, okay? And at that time, okay, we talk about how to understand these terms in a quantum mechanical way, okay, in a photon way. So every time you see a wave, okay, without conjugate, which that means your photon is annihilated, okay, it's annihilated. So annihilation of your photon meaning that your photon is consumed, and 2 photon at omega 1 is consumed, and then generate a photon at omega 2, okay, whenever you have conjugate, it means a photon is generated, is created, okay, another one at omega 3, right? So this process actually describes, okay, 2 of the photon from omega 1 is being get rid of, and then generate omega 1, 2, and 3. So it's like 2. It's like this, okay, this is 1, 2, omega 1, omega 2, omega 3, omega 4, right? So a pair of photons is generated, and 2, 2, and 3, and to satisfy energy conservation, then 2 photons at omega 1 is being annihilated, okay? So this process, because there's 4 waves, you can kind of imagine there are 4 waves involved here, so this is called 4-wave mixing. Okay, and often it's called 4-wave mixing. Okay, 4-wave mixing. And you can imagine, okay, this omega 1 doesn't really have to be, well, the two annihilated photon doesn't have to always have the same frequency, right? So what you can do is also, if you have, think about it here, there's other scenario is that if one omega 1 and another omega 2 is annihilated and then generate omega 3, one omega 3 and one omega 4 photon. This process also conserves energy, okay, also conserve energy. And whether it happens or not depends on whether it conserves momentum, which means the phase matching condition. And you can also imagine these two. Okay, so you can also imagine, other than this, you can also imagine these two waves can do the same thing as this process and then generate, another wave here, like two of the wave, it's like this, okay? Two of the photon is taken out from omega 3 and then generate another frequency. And this one can keep going. And sometimes people call this cascaded four-wave mixing. Okay, cascaded four-wave mixing. And one important thing is that all this frequency separation are the same, right? Are the same. So that the frequency of the output can be described as omega mu. Mu is a number, okay, equals to omega knob, it's the center frequency, times mu, the label. Okay, here we kind of mess up the label, but you can choose the center as 0, 1, 2, 3, minus 1, minus 2, minus 3, okay. Mu times the separation, okay, separation. And this is called a frequency comb, right, frequency comb. It's probably a better name is a frequency ruler because it's really like the grid on your ruler. You have an offset, and then all the rulers are equally spaced. And we've talked about this before briefly, is that this ruler can be used to measure optical frequencies. And of course, generation of frequency comb never really use two waves. Okay, it always start with many waves because that way you can, well, we'll talk about that really later, because that way you can really enhance the intensity in the nonlinear, in the Curry effect, and make this process very efficient. But one thing, well, right now you have, none of you have access to the lab, but when you return to campus, one thing you can do is that you can really have two lasers, okay, really have two lasers input into a long piece of fiber, and try to rank up the frequency a little bit. Sorry, rank up the power a little bit, and what you will see out at the output side of the fiber is that you will see two small waves here. Okay, you will see two small waves here on your optical spectral analyzer, and then you at that point you will know that I'm not lying. Okay, the entire process is possible. The four-way mixing is real, and of course this is very active research area because creating frequency comb is very important, and people, of course, constantly the discussion is how to make this process very efficient. Okay, how to make this the span as broad as possible so that you can measure lots of different laser frequencies. Okay, the lecture is probably too long, and thank you everyone. Enjoy staying home. If you're alone at your places, well, talk to your parents, talk to your friends, and enjoy a little bit of alone time. Okay,